first paper this evening is entitled Magnetic Field Mapping Between the Ionosphere and the Magnetosphere by Donald Fairfield and Gilbert Mead, and the paper will be presented by Fairfield.
As you are all aware, charged particles move easily along magnetic field lines. And in the magnetosphere, what this means is that if you have a measurement at one point, you're often interested in where that field line ends up if you would follow it to some other location. In particular, if you're interested in Magnetosphere-Ionosphere Coupling, and if you have a measurement in the ionosphere, you'd often like to follow the field line through that point into the outer magnetosphere to see where it leads to. This is a subject I would like to talk about today, and I'll do it by discussing a recent quantitative magnetic field model that Gil Mead and myself have developed. Now, of course, when you're near the Earth, an internal model is usually a good enough approximation. As you get further out into the magnetosphere, you have to take into account the external currents, and this is what we've been concerned with our model. I'd like to begin by saying just a little bit about the model. What we have done is to represent the disturbance field of these currents in the magnetosphere with a power series expansion, keeping terms through quadratic. And as an illustration, I've written one equation on the board here just for the x component of the disturbance field, and there are two others similar to it for the other two components. Now, our model is different from most other models in three respects. First of all, the power series includes not only the three spatial variables, but the tilt angle of the dipole relative to the solar wind direction. We feel this is important to get a realistic model of the field. Secondly, because of our methods, namely the power series, we do not require that curl of B be equal to 0 in the magnetosphere, as is often the case if one uses potential models, spherical harmonic expansions. So our model does include distributed currents within the magnetosphere. Thirdly, our model is based on experimental data in that the coefficients to our power series are determined by a least squares fit to a large body of spacecraft measurements. Now, on the first slide, I illustrate the model. Oh, okay, I see. Here's an example of the model in the noon meridian plane with zero tilt angle. And the solid lines here are field lines. The dashed lines are contours of constant field strength. And of course, it's a rather normal looking magnetosphere. Now, I should say that we have determined 4 sets of coefficients for 4 different levels of Kp. This happens to be our quiet model. As I said, for zero tilt. Now, on the next slide, again, we have the quiet model, but now for a 30-degree tilt. The solar wind coming in from up here, and you can see, let's see, this is the Earth-Sun line. You can see the field reversal region here is down below the geomagnetic equatorial plane. The next slide is the same field lines as that previous slide, only now we have contours of delta B, where delta B is the model field minus an internal field. It is a dipole-like field that doesn't take account of these external currents. You see, just point out a couple of features here. We have plus 50-degree delta B's up here, quite large. This is a point that's been emphasized by Segura in the experimental data from OGO, that you have these high field regions back here. You have weak field regions on the day side, delta B's of minus 30 up in the region of the polar cusp or clef here, and there's the tail. The plus delta B's are not nearly as as large in the southern hemisphere for this asymmetric case, the 50 degrees versus 20 degrees, say. And we have a top view is looking down on the equatorial plane for 4 different, well, the field lines originating from 4 different latitude circles. here's 70 degrees. There, you may be able to see two field lines coming out from every point here. One is for the quiet coefficients, another is for the disturbed coefficients. They're rather similar at 70 degrees. When you go to 75 degrees, they're separated a little more. But you can see the usual sweeping back of the field lines towards the tail here. Then when one goes to the higher latitudes, 80, 85, of course, the sweeping back is much more pronounced. One restriction of our model I should mention is we've limited our data to 17 Earth radii of the Earth. So the model is really only good within 17 Earth radii, and actually it's as you get out towards 17 Earth radii, there are a few difficulties also. Now I'd like to talk a little bit about some of the things we can deduce from the model. One can determine where the last closed field line is on the day side, for instance, by simply starting the equatorial plane and seeing whether the field line comes down to the Earth. And the various dashed lines here are what one determines for the four different models. That is the 4 KP ranges. The heavy line here is my experimental measurements from a few years ago. And the agreement is pretty good, I feel, particularly since the model was used with zero tilt here, and if one included non-zero tilt, these would all move in a little bit. If one scales off these distances from the Earth to the subsolar point here, and then one can plot them, that's the distance here, versus really KP. We have the 4 points here for the 4 sets of coefficients. Notice for the most quiet case there, the distance to the subsolar point is over 12 Earth radii, but for the most disturbed case, it's down here just a little over 10. Now, one can also, of course, determine the latitude where this last closed field line intersects the Earth, and that's shown down here. And again, for the most quiet case, it's up over 80 degrees, but for the most disturbed case, it's down here just over 76 degrees. Now, those of you that are familiar with the older models may realize that, I think all the older models, this distance was 80 degrees and up. It's very difficult to get this to lower latitudes, which one would really like to do in the view of other experimental data. Now, here I've tried to represent some of this three-dimensional information on a two-dimensional slide, and I'd like to take a minute to explain it here. First, look at the bottom portion of the slide. I've taken constant latitude circles here, projected them out to the equatorial plane along field lines. Of course, a dipole would project out to the equatorial plane as a circle, and when you're in close there, it is almost a circle. And as one goes out further, one sees more and more distortion. The dashed lines here are the constant meridian planes. Of course, a dipole would be radial, and so the curve here is due to the sweeping back of the field lines. Because our model is not really good out into the tail, on the top of the slide, I've projected the field lines onto a plane cutting through the tail at 10 Earth radii behind the Earth. So think of this as just a plane cutting through the tail, 10 Earth radii behind it. And again, one can see where the constant latitude, constant local time surfaces intersect this plane through the tail. Now, I won't say much more about this particular slide, but you see it's useful for taking any low latitude measurement and seeing where the corresponding field line goes to in the equatorial plane. So now I'd like to take some older experimental data you're probably familiar with, low altitude data, and use this type of figure to project it to the equatorial plane and the tail. Some years ago, McDermott and Burroughs looked at trapped particle data on a low altitude satellite and determined a high latitude cutoff for trapped particles. And they suggested that this was due to that the particles were trapped out to the last closed field line. And so here it's of interest to see whether the last closed field line of our model corresponds to what they would determine as the last closed field line. I've taken their outer line, their longitudes, and used my model to project those particular points to the equatorial plane. They are shown as the dashed lines here. And the heavy line here is the last closed field line of the model. So to the extent these dotted lines go out to the solid line, there is good agreement between their data and the models. And you can see they come pretty close here. I've also taken some data of Winningham. He had published upper and lower boundaries to the polar cleft as a function of longitude. In other words, he determined the field lines which you would like to trace to see where they go to see if they go out to the polar cleft. And indeed, that's what I've done here. And the shaded region here is this band of field lines that identified by Winningham. You can see they fall just inside the model here. But when you consider the KP range that he has defined here versus the KP range for this particular model, it makes pretty good sense. I mean, they come out pretty much where you would expect them, close to the magnetopause. The next slide, this is really the same figure, only now I've added some data of Evans and Stone. Now they've determined the low latitude boundary to the polar cap. And of course, one would expect the low latitude boundary to the polar cap to be equivalent maybe to the high latitude trapping boundary. And these open circles on here are the Evans and Stone points. You can see they do agree pretty well with the McDermott and Burroughs points back here in the tail. So there's pretty good agreement on that score. The next slide is similar, only for a different KP range. Again, it's the data of Winningham here. Here I've used the projection in the earlier slide, the bottom view being the view from above the pole, the top view, the plane intersecting the tail, and done the similar projections of the polar cleft. Here you see that it projects all the way out to the magnetopause, to the last closed field lines, and beyond, where the beyond means that the field lines go back to the tail. So you see a ring all around here from the field lines. Here's the same figure where, again, I've added the Evans-Stone data, the identification of the polar cap with this shading here. And of course, as one would expect, the polar cap projects to the tail. What's interesting here, I think, is this shape here. What isn't polar cap, of course, is at a lower latitude would be plasma sheet, probably. And this this shape here is very reminiscent of the Vela determinations of the plasma sheet. Let's see, this is a convection pattern you've seen a lot of today. I projected the sunward convection region. That's what's shown by the shading here. Both the Hepner's data and the Kaufman-Gurnett picture, which is quite similar. Since I'm running short of time, let me just point out that most of the region outside the plasmapause and inside the magnetopause, of course, is the sunward convection region. We can't really say if the sunward convection, or if the convection is sunward all the way out to the magnetopause or not. I think that's an important question, but it can't be answered by this method. Here's the harangue discontinuity projected out. There was a question on this morning. Here it is projected with my model. Finally, these field lines from the synchronous orbit for 3 different tilt angles. I mean, if you had a dipole, they would project out as this line here. You take the distorted field model, you get a diurnal variation here depending on the local time. In summary, just let me point out that these models are all static models. However, we know that certainly the real field is not static. So the models are primarily of use in projecting average data. One must always keep in mind that the field is actually very dynamic. I just want to emphasize this point, and because I feel it is very important, and certainly the models cannot take into account the rapid changes that do occur during substorms.
On this last slide here with the geostationary orbit, now you're starting with that projection with just a circular orbit at 6.6 and projecting it to the ground with your model? Is that what you're doing?
That's right. This is a point in the geomagnetic equatorial plane. Of course, the synchronous satellite won't necessarily be in the geomagnetic equatorial plane. This isn't really a diurnal variation either. It's really it's the foot of the field line is a function of local time, but in a real situation, the tilt will change as the Earth rotates, of course, whereas these are for constant tilts. So, but of course, this could all be done for a more realistic situation.
That is possible. I mean, you could take a given longitude and for a given satellite and predict that.
Oh yes, that's
Okay.
something I've been meaning to do for this. What's the coming launch? ATS. Yep, that's right, and GEOs also.
In those middle slides, well, 3 or 4 slides back, you showed a solid curve in there, the smooth curve. Back 3 or 4. Back some more, several more. But doesn't seem to be going back.
There we go.
A little more. You showed the smooth curve that looked a lot like the plasma pause there. Was there some particular reason why you... One more back. One more. May see the whole talk again here. Whole series there, where you showed that solid curve. It says smooth boundary. What was the purpose of putting that in?
Oh, yeah, I didn't have time to talk about that. The smooth boundary was another boundary determined by McDermott Burroughs. Well, what they suggested was that outside the smooth boundary, pitch angle diffusion was important. I simply included it in here as another parameter, I mean something else to map. This is a average plasma pause in here, of course, and it seems to fall outside the plasma pause.
Yeah, my question was the axial asymmetry that Seguier reported. Do you see that in your model, that afternoon bulge in the field?
Our model, we did impose symmetry, both north-south symmetry and east-west symmetry. Originally, we started out without imposing such symmetries. And of course, you have many more coefficients in your expansion. And when we did it that way, we didn't see any north-south, either north-south or east-west symmetries that we felt we could have confidence in. Therefore, we thought it best to eliminate them altogether. We have looked at our data. I guess you're talking about the declination asymmetries of Seguier?
The afternoon bulge that Seguier reported in the, I guess it's the ATS-5 measurements.
Oh, let's see. Maybe you're thinking of something different. Bulge. You
called it
let's see. When you say bulge, you must mean depressed
bulge
fields.
In the field. Depressed fields. Yes, in the field.
Let's see. Is that part of the declination story? You know,
Delta B.
Delta B. Well, I guess I'm not sure exactly what you're
Well, the
referring
reason,
to there.
the reason
There-
I make
I
a
mean, there's-
point, the reason I make a point of it is in comparing the plasma pause at low latitude or at high latitudes or mid latitudes at lower altitudes with the behavior at the equator. We've used an internal model of the field based on the internal sources, and therefore don't very accurately map the field lines at L equal to 4 or 5 out to the equator. The question is, could we be making a large error in the position of the field line, the L value of the field line, by doing that?
Yeah, so I think that is a very good question. I was thinking about raising that question myself, although I don't know the answer. I think there is a possibility that may be a problem. This talk yesterday about the trough at low altitudes versus the plasma pause far out raised this question in my mind as to whether some of these problems could be due to the use of an internal model. And I don't know what the answer to that question is, although I think it certainly would be worth looking into.
Just one comment about your mention of prior models and the last closed field line. I believe the image dipole model, one of the oldest models, can be matched to give last closed field line as you have or even lower if you want, just by using the right dipole moment for the image.
It's okay. That's unusual, and most of them cannot. Certainly.
Could you say a few words about the accuracy of this model compared to that of the competition, the Olser-Pfizer model? Under similar conditions. I mean, you have tilt and they don't or something, isn't that right?
Yeah, yes, that's true. We haven't done any direct comparisons with their model. We do feel that's probably the big advantage of our model. In fact, it does have tilt, whereas theirs doesn't. They certainly do a better job on the tail. I mean, our model doesn't purport to describe the tail in any sense. I mean, it's good, particularly well. We say certainly not without. I mean, certainly not good outside of 17 Earth radii. I mean, theirs can go way back in the tail. I think those are the big differences.
Yeah, one thing they've been going around saying is they predict the cosmic ray cutoffs quite well. Have you checked any of those numbers? I think they would probably be affected more by the tail than, say, the 35 keV particles.
We haven't done anything with that. No.
You mentioned that the curl of B was 0, but how about the divergence of B?
Divergence of B is built into this. It is 0. Yes. Yes.
I'd just like to put in a bid for you to add to the list of synchronous satellites. You mentioned ATS-5. We're about as far from the geomagnetic equator as one can get on ATS-5, and we have a crack at doing some mapping in the dynamic situation by comparing particle data with ground observations, and it's been very frustrating in that all of the models list the projections from the geomagnetic equatorial plane as a convenient tool for experimenters on synchronous satellites, and none of them are useful because of that.
Yes. Well, certainly that can be done with this model. I should maybe make another point along those lines. Our data also only came into roughly 5 Earth radii. This was the thresholds on our magnetometers. So we don't describe this depressed field region near the equator inside of 5 Earth radii, the work Segura has done. And this would place some limitations on the model also.